Hey guys. Last week we talked about sound, and this week we are going to be transitioning into light. And light is actually in many ways very difficult to directly observe, so it took us a while to kind of discover the nature of light. So we're going to start slowly with the basics, then talk about how light can be modeled as a wave in many instances. And then next week we're going to talk about color, what causes you to see certain colors, and how your eyes work. And then last, we're going to end on some of the flaws or some of the ways in which light is an exception to the wave model, and so some of the stranger things about light. So that's sort of where we're going with this, so you have an idea. First and foremost, like, remember physics, we're always talking about how things move. So it's like, how does light travel in general? Like, that's sort of the first question. And often the most common, if you just ask people how does light travel, usually people talk about it spreading out or like traveling in a cone. Other times people will say that it's traveling in a straight line. Now, I think where this idea of a cone comes from is just a flashlight, right? Like, most of the time we have lights, in our houses, or there's the sun, candles, whatever. But when we have control of the light source, the flashlight is usually what we have. And so you see, as it looks here, it looks like the light is spreading out, and you've even got kind of a dimmer part of the cone here and here. And so I think that's where it comes from. But it turns out that this is actually flawed, because the flashlight is actually designed to spread out light, and it has this sort of cone shape at the beginning to send light out in that direction so that it lights up most of the things in front of you. The idea that light travels in this cone is actually pretty easy to disprove. You just need a light source. It can be a flashlight or a light bulb or a candle or whatever. And then you have to be looking on the other side, and in between you put 3 cards with a little pinprick hole in it, okay? And so if light traveled in a cone, you would expect the light, it would go through this first hole right here, and then it would spread out in like this cone shape. And so that would mean I could move card B wherever I wanted it to be, and some light should still get there. Maybe it wouldn't be as bright, but some light should still get there. But if you do that, your eye can't see anything. You don't have line of sight to the candle, and it doesn't work. So it turns out that light does in fact travel in a straight line. Okay. And I, as always, never want you to take my word for it. So here is a demo of someone doing this in actuality so that you can see it.
Hi, welcome to Science for Schools. Today we're going to be investigating how light travels specifically. Does it travel in a cone? Is it a straight line? That kind of thing. So what we're going to need is a light source here. We have these 2 pieces of cards. Each of them has a hole in it, and I'm holding those in place where retro stands. I've also got a third similar piece of card with a hole in it as well. So what I'm going to try and do is line everything up. Okay, so things are lined up perfectly now. You should be able to see the light coming through the holes in these pieces of card, but you can see if I move one of these out of the way, then suddenly you can't see anything anymore. If I move this back, and things line up perfectly, the hole in the first card, the hole in the second card, and the light are all in the same line. And you can see the light. So what I'm going to do is I'm going to take a third piece of card with a hole in it, and if I put that in the way of the light, suddenly you can't see anything anymore. But if I position this just right, if I line up all 3 holes perfectly, then suddenly you can see the light again. So it only works when all 3 holes and the light source are all in one line, and that is proof enough that light must travel in straight lines.
Yay!
So thanks.
And as you can see here, like, your eye has to actually be part of the line, right? So if your eye is not part of the line, you can't see the light either. So if you're off to the side, like if he had the camera in that video in a different position, you wouldn't have been able to see the light. So that means in order to see anything, like any object at all, light has to actually enter your eye. But that means that every single object that you can see has to have light bouncing off of it. And we call this reflection. The idea is you have some kind of light source. In this case, it's like the sun. That light hits the object, and then that light bounces off. Okay? That's what you can see. Okay. Now, it turns out that your eye is a little bit more complicated than that because every object has multiple light pieces of light coming off of it, or waves of light coming off of it. And so this right here is the pupil, this little circle right here. That's like the black part of your eye. Now, the black part of your eye is not actually like a surface that is black. It is a hole in your eye that lets light come in. Now, you do have a lens over it to protect it. And the lens also allows you to focus on things that are different distances away. But the pupil is what allows light to come in. So lots of rays come from all over this object. But the idea is light from the top will enter in and go in a straight line this way. And light from the bottom of the object will enter and go in this way. And it will project an image on the back of your eye. And if your eyeball is misshapen or anything like that, that's what causes, for you to be nearsighted or farsighted. There's lots of different types of misshapen abnormalities, and we can correct for most of that. But you do actually see upside down. Now, then your eye sends that signal to your brain, and your brain is like, hey, why is everything upside down? And so your brain just flips things right side up. And your brain is pretty smart about that. You can actually wear goggles that invert everything and make you see everything upside down. And it only takes your brain a couple of weeks, 2 or 3 weeks, before it will just flip everything again. It's like, why are we looking at the world upside down all the time? And then, of course, if you take off the glasses that make you see everything upside down, you then have to spend another 2 weeks for your brain to readjust and flip it again. But yeah, your brain is pretty cool that way. Now, then the question becomes, if light is reflecting off of every single object, why don't you always see your reflection rather than the object in question? And so the answer to that is the so if a surface is really smooth, like nothing is. Mirror, because a mirror is very smooth, or like a large body of still water, like that kind of thing. Most objects are not that smooth, and they're more craggly, and so when light hits it, it bounces off in every which way. And so this causes the light to be reflected in very scattered ways, right? And so that's what we actually call it. We call it scattering. So light tends to scatter off of most surfaces, which just means that it is reflecting in every single direction at the same time. Whereas a mirror reflects all light that's hitting it in the same direction. So that's how you can get a coherent reflection. Okay. Now, if you're doing this off of like off of a surface, like if it's reflecting off of it, this is another image where it's like the light ray comes in, it hits the thing, and then it bounces off. And so if you're over here, you can see that there was light at this point. Okay. Whereas if a light hits a surface that is not smooth, it kind of hits it and it scatters it in all directions. And so you can see those things. Okay. So if a surface is scattering light, you see a bunch of light from a bunch of different locations, and your brain can't make an image of something else reflecting off of it. It only allows you to see that object in particular. Okay. So this is another video here, and it shows you again that light travels in a straight line. They actually come up with a cool visual to show you that the light is going in a straight line rather than a cone, and you can't see that light as it's traveling through the air unless it can hit your eye. So it has to have something to bounce off of in order for it to get into your eye. Here we go.
I am now shining a laser beam at Krista's blouse. You can see the red spot reflecting from her clothing, but you cannot see the beam from the side as it travels from my laser pointer to her.
So what he means by that is just that, like, even though the laser is currently on, you can see where the laser hit and it bounced off in every direction, so you can see that. But the light that traveled through the air has nothing to bounce off of, so it's not entering your eye, so you can't see that it's there. Okay.
But now, Chris is going to put some chalk particles in the path for us. The light now scatters from the chalk dust, and you can see the beam.
Whoops. Dang it. Let me get back to that spot.
In the path, it now scatters from the chalk dust, and you can see.
So the idea here is what he means by that is now that there's dust in the air, that laser beam can hit particles that are just floating around in the air, the chalk particles, and then they can bounce off. They're being scattered in every direction, so now you can see that laser beam. Also notice that the laser beam is in a beautiful straight line.
See the beam.
Great. So far, we have established that light travels in a straight line, not in a cone, and that light scatters off of most surfaces, which means it reflects in every direction, and that's how you see those things. And light reflects coherently off of smooth surfaces, and that's when you can actually see your reflection. And then remember, the last point that we want to keep in mind here is that we can only see things because light bounces off of them and into our eyes. If the light doesn't get to our eyes, we can't see that object, which is why you have to have line of sight in order to see that something is there. And you can't see around corners, that kind of thing. This is the first part. I'm going to actually break this up so that if you want to review this lesson in the future, you can just go to whichever part of the lesson you need to review. So part 2 is up and coming.